Let us discuss about the quality of vapor after compression. That is, whether it may be wet, it may be dry or supersaturated. Supersaturation means super dry vapor. So we are having in vapor compression refrigeration. There are three parts. That is vaporization, compression, condensation, and expansion. So here in this case, when after the compression, if the let us discuss what happens when the vapor condition is wet or vapor condition is dry or vapor condition is superheated. Let us consider this TS diagram, that is by plotting the graph, that is on a TS diagram, that is temperature entropy diagram. Let us discuss the quality, what the quality of the vapor we need to have. That is by discussing this by applying on the temperature entropy diagram. But first of all, by representing this vapor compression cycle on TS diagram, we'll consider first the when the vapor is dry and saturated at the end of the compression. By considering this TS diagram, so the vapor compression cycle is shown on the TS diagram. The state points A, B, C, D represents the points in the encode shown in the flow diagram. At low pressure and low temperature, T2 vapor enters the cylinder of the compressor. So here in the compressor, the T2, the temperature is T2 at point A, and it is compressed to maximum at T1. Right now, vapor enters the cylinder of the compressor where it is compressed adiabatically to B, thus raising its temperature to T1. That is from T2 to T1. This T2 is lower temperature. This is T1 is higher temperature. Right now, it is then condensed in the condenser along the line BC, and in doing so, it gives the latent heat to the condensing medium. That is, here, this is the condension process. B to C is the condension process. So, totally the temperature remains same in this thing. That is, this is the T1 temperature, right? CD represents CD represents the throttling expansion of the liquid refrigerant through the expansion valve to the low temperature T. It will be noticed from TS diagram that a part of liquid refrigerant vaporizes as it passes through the expansion valve and its drainage fraction is D. See, in this thing, this is the condension process and this is the expansion process. See, actually, this is the expansion process. But in this TS diagram, we can notice there is a drainage fraction while this expansion process taking place. That is QD by QA is the drainage fraction here. See, it will be noticed from the TS diagram that a part of liquid vaporizes as it passes through the expansion valve and its drainage fraction is D and is represented by the ratio QD by QA. This is QD by QA. This is the drainage fraction. Right? At D, refrigerant enters the evaporator where it further vaporizes at on slant pressure and temperature and takes its latent heat from the refrigerated space through walls of the evaporator. The process of vaporization continues up to which was the starting point, and thus the cycle is completed. Now, work done by compressor is equal to W is equal to area ABCD. ABCD. This is the actual work done by the compressor. Then refrigerating effect is equal to heat extracted during this. That is dA. dA is the refrigerating effect. That is area under dA. This includes dA this is the work done area. So area dA divided by ABCQ. ABCQ is equal to the coefficient of performance. Since CD is the throttling expansion, therefore total heat at C is equal to the total heat at D. So this is the throttling process, and the heat at C is equal to heat at D. Thus, Hc is equal to Hd. This is the temperatures, and H is the entropy at this point is equal to this point. So this is the perpendicular to this is same, and if perpendicular to this is same. So entropy at here and entropy at here is equal to same. That is Hc is equal to Hd. That is this falls on the same line, that is entropy line. So H is equal to Hd. Then the coefficient of performance can be expressed as COP is equal to HA minus Hd. That is HA minus Hd and HP minus HA. So Hd is equal to Hc means, so this will comes HA minus Hc divided by HB minus HA. So this is the actual temperature entropy diagram for the vapor when it is in a dry state. See here in this case, this B will fall on this point and this A will be in this. So when suppose let us consider what happens when the vapor is wet at the end of the compression. So in the last case, when the vapor is dry, this point B falls on this line. Okay, so when vapor is wet, it will fall below this line, that is entropy line. So this B will shifted to B dash here. So the remaining thing is same, that is compression, condensation, expansion and vaporization will be same as it is, and also you will find the dryness area here, and dryness factor is equal to Q by QD, and here what happened, the only thing is these points, that is A is shifted, the point which is come here, the point which was supposed to come here will be shift to this point. A, B and B shifted to B dash and A shifted to A dash. So this falls within the wet line. This is the wet region. This is the supersaturation region, and this is the dry region. We know from the TS diagram. Always this line, you see this line is dry saturated line, and with anything which falls on this line will be supersaturated. Anything which falls on this line will be saturated, and anything which falls below this, that is wet region, is said to be wet region or wet steam or wet vapor. So in the last case, the vapor is dry, this will be the case A, B, C, D, and this is the dryness fraction. And here in this case, see, if the vapor is dry, it will falls on this line only. So this is the actual process which is taking place when it is dry. Say, in this case, second case, when the vapor is wet, it will fall below the wet region. And in case of supersaturated region, say this will be shifted to here. So somewhere, if the steam after compression is if the vapor after compression is supersaturated, it will fall here. So this is the A is shifted to here, and this B will be shifted to the saturation region. So this is the reference line. That is saturation line is the reference line, and this will be shifted to here. So what happens in the three cases? That is, if the vapor is super saturated, this will be the condition. That is, the points in a TS diagram will fall on the super saturation region. And if what to be wet vapor, it will falls on the wet region. That is, this is the dry saturation line, this is the wet line, this is super saturation line. It will falls on the wet region. That is when the vapor is wet. If it were to be dry saturated vapor, it will fall definitely on the saturated vapor line. So the conclusion of this is why we are going to study this temperature entropy diagram for three conditions, that is for wet vapor and for the dry vapor and supersaturated vapor, is because we need to have a condition of the vapor after compression must be saturated vapor. It should not be either wet vapor or it should not be a supersaturated vapor. In actual practice, dry compression is preferred as there is a higher volumetric efficiency and mechanical efficiency and less chance of damage to the compressor. So we are considering this thing, that is we are studying this temperature entropy diagram on the wet, super saturated and vapor, dry saturated vapor regions, because in order to have good efficient performance of the refrigerating machine is the vapor after compression is required to be as a dry vapor. That is, the vapor which after compression is needed is a dry vapor in order to have good volumetric efficiency and good mechanical efficiency and low effect on the compressor. Okay.